Okay, so first the bad news about the Monday lecture. We were supposed to shift it to 9:40, but unfortunately we cannot. There are no empty classrooms. So, I mean, if you want, we can start at, I don't know, at 8:50 or 9 without giving a break. I also think so. I mean, so let's stick with 8:40 and try to be here at 8:40. Okay, now back to your questions.
Can we ask one more question? Can we ask one more question?
Oh, we can. You should first give me your homework. So what's your question about the homework? Which is? Well, you see, just like, I mean, when the course finishes, you forget most of the things that you have learned in the course. Just the moment that I upload the homework, I forget everything about the homework. So you have to tell me what the question is. Or what is it that you didn't understand?
Calculations.
Calculations. Well, they are tedious, but straightforward.
The electric field, given find the electric charge density for given electric field.
Okay.
This is the question.
Okay. So let's say a different example. Let's say that the electric field, this is equal to Q over R squared in the R hat direction if R is larger than R and 0 otherwise. Well, this is a simpler version of the homework questions, but the idea will be basically the same. So what do we know? We know that the divergence of the electric field, this is equal to 4 pi rho. Now, there is a discontinuity in the electric field. So we can take the derivatives away from the discontinuity. Now, so let's 4 pi rho at the point R. Let's take the divergence of the electric field, divergence of, let's say, R hat over R squared for R larger than capital R. We know that this is 0. Well, we know that that is proportional to Dirac delta, but the Dirac delta at the origin. But since we are not at the origin, we are at a distance larger than the capital R. Divergence of the given electric field is 0. So that tells me that the divergence of the electric field everywhere is 0, except and possibly R is equal to R. Because that's the point where we have the discontinuity. Basically, you can imagine it as a step function. You can say that, okay, the electric field is Q over R squared, the step function R minus the capital R in the R hat direction. You can also think of it in this form. Now, let me write it slightly different. It's the product of two functions. When you take the derivative, basically you have the derivative of the first part, which is Q over R squared in the R hat direction, times the second part. While the derivative of that, meaning the divergence of that first part, is 0. But then you also have contributions from the derivative of the step function, which would give us some Dirac deltas. So that is what we would expect. We would expect some surface charge distribution located at the surface of this sphere. And we had also discussed that the electric field, the perpendicular component of the electric field, there was a discontinuity. And this discontinuity was equal to 4 pi times the surface charge. And the parallel component of the electric field was equal to the discontinuity in the parallel component was 0. It was discontinuous. It was continuous. So we already know from this argument, just looking at the divergence of the electric field when R is not equal to capital R, that there is no charge anywhere else, except that maybe on a surface. And we also know that the electric field is not continuous. But since it is not continuous, tells us that there is a surface charge, which we also expected from this derivative of the step function argument. Now we can determine this surface charge. You see, this is R. R is equal to R. Okay. At any point, the parallel component of the electric field is equal to 0. Electric field is radial or 0 everywhere. But radial means it's perpendicular to the surface at every point. So there's no additional restriction from this, the requirement of the continuity of the parallel component. Now the perpendicular component of the electric field, on the other hand, this is equal to Q over R squared. The radial component is the perpendicular component. And then we have the step function, which says that inside the sphere it is 0, outside the sphere it is non-zero. So the change in the perpendicular component of the electric field as we cross the boundary, it is given by Q over R squared. Now I replaced the small r by large R because we are just looking on the boundary, which is at small r equal to large R. And we know that this should be equal to 4 pi sigma, or sigma is equal to Q over 4 pi R squared. Well, this is basically the known result. We have a charge Q uniformly distributed over a sphere. And we know that this uniform spherical charge distribution creates 0 electric field inside, and outside the sphere it just behaves like a point particle. So here we have that this was the electric field, and we had figured out that it corresponds to a spherical uniform charge distribution distributed over the sphere with radius capital R. Now in all the problems, this is basically the idea. So you should first calculate if you want to find the charge given the electric field, you first have to study the divergence of the electric field. And the divergence of the electric field will give you the volume charge density. And then you should study also whether there is a discontinuity in the electric field. And by looking at how the discontinuity of the electric field, you can determine what is the surface charge density, if any. So once we know the electric field, we can determine the charges. You should be able to determine the charges given the electric field. Or, for example, in one of the questions, which in the first version of the homework it was not correct, and I updated the homework, I think, twice. The electric field was given by this expression. It was equal to Q over 4 pi epsilon 0, R over R squared. Now there's no epsilon 0, there's no 4 pi. In the radial direction, if R is less than large R, and it is Q over R squared in the radial direction if the radius is larger than this sphere. It is similar to our previous problem. Now first, always we have to evaluate the divergence of the electric field. Now the best would be to use spherical coordinates. And in spherical coordinates, the divergence of a vector field is given by the derivative of the radial component with respect to the R, plus we have other terms. Now since we only have the radial component in this electric field, this will be the term that I will be interested in only. And if you calculate is this correct? See the divergence in spherical coordinates. Okay. 1 over r squared times r squared ER. Okay, so this is basically why the second term, this q over r squared in the radial direction, gives me 0. When we multiply with r squared, it just becomes a constant. Taking the derivative, it is 0. So this becomes, well, it is 0 if r is larger than r. And when inside our sphere, it's just proportional to r. If you take the multiply with r squared, that becomes r cubed. Taking the derivative, that is 3r squared, which cancels with this 1 over r squared, so it is 3q over r squared. So this is the third component, r cubed. So this is the divergence of the electric field.
Why r cube above? R is a constant, capital R is a constant.
Capital R is a constant, so if you just put small r is equal to capital R, I would like to have a continuous electric field. So that's why it should be r cubed.
Okay. Down there should be r cubed.
Yes. And, well, there's no discontinuity in the electric field. The electric field is continuous, so that basically tells me that there is no surface charge anywhere. And then we look at the divergence, and the divergence should be equal to 4 pi rho. So the charge density is equal to 3q over 4 pi r cubed. I also have a step function. This is only when small r is smaller than capital R. Or let's write it in a different form. This is q over 4/3 pi r cubed. Well, 4/3 pi r cubed is the volume of my sphere. So this is nothing, well, the charge density is uniform. It is a total charge q uniformly distributed over my sphere. And no surface charge. Well, of course, we could have, let's say, put some constant over here, let's say 1/2. Then the 1/2 over there, if we had put 1/2 over there, we would have an additional 1/2 over here. So the charge density will have an additional 1/2 and q over 2 over here. But now the electric field would be discontinuous. There will be a jump in the electric field on the surface of my sphere, which will just tell me that there is a surface charge. And so I would have a volume charge plus a surface charge.
So there should be an addition to.
Hmm?
This is not
Yes.
important.
This will be no longer correct. There will be plus a surface charge. Which we should calculate. Well, it will be a q over 2 distributed over the surface uniformly. Yeah, basically because I'm not changing the electric field outside, but I'm just lowering the electric field inside to half of it. So for an outside charge, it should still see a total charge of q. Q over 2 is uniformly distributed over the volume. The remaining q over 2 should be on the surface.
trapped one.
Yeah, this is the surface charge density. I'm not talking about the volume charge density. Of course, I can relate the two. Yes, other questions? Yeah, these are your questions. So if you don't ask, I will ask your questions.
Can we take integral of direct delta at one point?
At one point,
Or choose an interval that boundary is the zero of direct delta?
well, if you do that, there is an ambiguity. If you say that the Dirac delta is on the boundary, well, you should be taking some kind of a limit. Then the question is, are you taking the limit that the Dirac delta moves to the boundary within your interval, or from out of the interval, or, well, it's an ambiguous situation. In that case, you have to look at your physics problem, and in nature we don't really have these Dirac deltas. So they are kind of a limit of certain situations. So you should consider your situation and determine whether you should take the Dirac delta to be inside your volume, or inside your interval, or outside of your interval. Now, one example of this one would be, for example, if you put a point charge at the center, at the origin. We said that we can write this as Q over R squared delta R minus large R delta theta minus pi over 2 delta phi minus phi sum phi 0. Now large R is 0. Now, when you put this in any integral in spherical coordinates, you will end up having the radial integral going from 0 to infinity. So your Dirac delta is non-zero on the boundary. But now, of course, in this case, we know that the Dirac delta is in our volume. All of it is in our volume. So this integral, we should define it to be 1. In this case. In certain cases, you have to define such an integral to be 1/2. In other cases, you have to define it to be 0. You have to look at the physical case to determine what you should take for your Dirac delta. In this case, I know that all of my charge is in my volume. And since I happen to choose the origin as the position of my charge, that is kind of a singular point, and hence I have this ambiguity. To resolve the ambiguity, I say that, okay, this Dirac delta R is within my interval, although it is on the boundary.
From one point we can get the limit.
But which kind of limit? I mean, you see, if you, in general, for example, let's say from A to B, dr Dirac delta x minus x0. Or let's say Dirac delta x minus a. Dirac delta is on the boundary. Well, you should look at it as a limit. But which limit?
I mean, for example, there instead of A and B, A plus epsilon, A minus epsilon, then limit of when epsilon goes to 0.
Well, you see, if you say that from A minus epsilon to A plus epsilon, then you already say that your Dirac delta is in your interval. You are already taking the limit, defining the limit. But you could have also said that Okay, let's take this limit. A plus epsilon to b. In the limit as epsilon goes to 0, this is again an integral from a to b, but its value is different. So which limit you should take depends on your physical case. Yes, other questions? Well, one of you have this question. So we had studied this parallel plate capacitor, which is we have a plus sigma charge over there, we have a minus sigma charge over here, and a layer separation d. Now, if you take the limit as d goes to 0, this is just a dipole layer. Sigma goes to infinity, d goes to 0, such that sigma times d is finite. This is our dipole layer. But we know that outside this dipole layer, the electric field is 0. So doesn't this dipole layer create an electric field outside?
D goes to 0.
Can that be zero?
You see, we take this limit. Sigma goes to infinity, d goes to 0, such that sigma times d is constant, goes to some constant.
If the area is infinite, then
Why not?
because then the positive charge and the negative charge should cancel each other's electric field.
But you see, in the case of the dipole, we said that the electric field or the potential, they will be proportional to sigma times d. Of course, if you just take the limit d goes to 0, they will cancel each other without taking sigma goes to infinity limit, and they will cancel, as you said, and we don't have any electric field. But we are taking the limit as d goes to, as we are taking the limit d goes to 0, at the same time we are taking the sigma goes to infinity limit, so that the sigma times d is constant, so a dipole layer in general will create a potential. And we had also written down the expression of the potential. At least we said that the potential of a dipole layer at the point r was equal to dipole density times d omega. D was sigma times d, whichever value you fixed it at. Of course, the limit d goes to 0, sigma goes to infinity, and d omega is the solid angle that from your point, this dipole layer spans. So are these compatible? We also know that the electric field here should be 0. That is, in the infinite plane, for an infinite uniform capacitor, we said that the electric field outside the parallel plates is 0. But at the same time, there is a potential created by this dipole layer. Are they consistent? I mean, they should be consistent with each other, because a capacitor is nothing but in this limit, a capacitor is nothing but a dipole layer.
These are same. Capital D's are same.
Okay, so so what is the potential at this point, let's say? Let's call this R0, this point R1.
4
Hmm?
4 5 sigma, the difference.
What is V at R0? Or let's say V of R0 minus V of R1.
So basically you should have some infinite value for the electric field between the
True.
two plates.
Mm-hmm.
So across these two plates, even though we have small distance, the potential drop
There will be a potential drop, which will be,
4 pi sigma.
do you agree? 4 pi sigma? Well, if it is 4 pi sigma, remember, we are taking the limit that sigma goes to infinity.
4 pi t.
So this is divergent, 4 pi sigma, d. So this is the potential difference across the plate. What is the electric field above or below? How?
Above.
Above. Electric field, let's say at R0. What is the electric field? How do you see that? I mean, you see, is it consistent with this expression over here? That's what I'm looking at. Well, we can set the potential at R1 to be 0, for example. Then we see that the potential at R0 is non-zero. So how do you see that the electric field is still 0, although the potential is non-zero?
Take the gradient with respect to R0, with respect to R1. They will both be big, unless if R1 and R0 are between the two plates.
So this is basically what you are saying, right? Electric field is minus the gradient. Well, R1 is just constant, so that's why I can put it inside this gradient. It will just give me 0. I'm calculating the gradient with respect to R0. If I shift R0 slightly, the potential doesn't change, but that basically tells me that the electric field is 0 because D is constant. So you can treat this capacitor as a dipole layer. It doesn't create any electric field though, since it's uniform. Of course, if you have the bands or if the dipole layer is not infinite, if you have a finite capacitor, then the potential will depend on your position. This is for the infinite capacitor. So if you have a finite capacitor, why does it depend on the position? How can you say that, looking at this expression, how can you say that it depends on the position? Since the potential depends on the position, the electric field will be non-zero.
Because the solid angle for the first plate is not the same as the solid angle for the other plate.
Well, you see, if you take the limit d goes to 0, the solid angles will be the same. In that limit, they are the same. You see, what we are looking for is that the solid angle should change as we change the position. Does it? For a finite plate. This is our finite plate. Plus sigma, minus sigma. Let's say we look from here. So does the solid angle depend on this point R? You see, on one hand, we have this finite capacitor, so there should be some fringing effects. So the electric field outside this capacitor should not be 0, which means that the potential should change from point to point. If we still assume that sigma is constant, by the way, if it's a conductor, sigma will not be a constant, but let's just assume that it is constant. We somehow fix it to be a constant. So if there is a potential, D is constant, so the solid angle should not be constant. The solid angle should depend on our position if the potential depends on position. That's the only way. Does it depend on the position? How?
change, if you change R and connect with lines to the boundary of the layers, so that solid angle will be different for different positions.
The angles change, as your friend points out. So you see, for this position R, this is basically our solid angle. Just imagine a three-dimensional cone. If you take a point somewhere over here, it is now, again, just imagine a cone. It is that angle over there. It is smaller. So as the distance gets larger and larger, the solid angle becomes smaller and smaller. Now, furthermore, if you, not even larger and larger, for this point over here, this is the solid angle, which is very small, although it is very close to the capacitor. So the solid angle does change from point to point. Hence, this expression over here, first of all, it does take into account the fringing effects. They are not ignored. This is exact. And secondly, it does predict the, at least in the finite capacitor case, it does predict the fringing fields. But of course, this finite capacitor is not a point dipole. So you cannot really use the expression V is equal to P dot R over R cubed. For a point dipole, that is the potential. Well, for a capacitor, well, of course, if you are very, very far away from the capacitor so that the area is negligible, in that case, this will be the form of the potential. But close to the capacitor, it won't be the case because this is for a point dipole or an ideal dipole. So what's an ideal dipole? What's a dipole and what's an ideal dipole?
Same amount of charge with the negative sign. This is like,
Okay.
I don't know, is something like that, same amount of charges, but the distance between charges negligible related to our points of interest.
That's a dipole. What's an ideal dipole? Well, an ideal dipole is basically this system. Now, this is a dipole, plus Q minus Q. And we know that if you are sufficiently far away from this system, sufficiently far away meaning that the R is much larger than D, then you can approximate it by this potential over here. But you can take the limit as Q goes to infinity, D goes to 0, such that Q times D is constant. So if this is the case, then every point is much larger than D. So this expression will be true at every point, not just sufficiently far away. But that basically means that, well, this is what's called an ideal dipole. Of course, it's an idealization. It's not a realistic case. But as long as you don't go very close to a dipole, you can treat every dipole as an ideal dipole. Still no questions from you? So what's the Bayer-Coulomb potential? Bayer-Coulomb potential. And the other alternative? Well, sometimes you will see that it's called dressed or screened Coulomb potential. Now, this was discussed in the atomic case.
Plus charge is screened by minus charge, say electrons.
Yeah, basically what you have is, okay, this was our picture of the atom. We had a nucleus, and we had an electronic cloud. So if you put an electron over here, it sees two effects. One, there will be an attraction, the positive charge of the nucleon, plus there will be the repulsion of these electrons, the electronic cloud. So it will not really see the full nuclear charge, but a smaller charge. So that's what we call the screen charge. So that is the screen charge. So you have a point charge. It is screened by other charges in the near vicinity. It will be especially important when we study the electric field in matter, because when you put some charge in a matter, what will happen is, let's say you put a positive charge inside any matter, it will basically attract the electrons inside the matter. If it's a conductor, the attracted electrons will completely neutralize this charge in the center, so that there won't be the screening will be complete. There will be the Bayer-Coulomb field of this positive charge, plus the additional Coulomb field due to these attracted electrons, which will completely screen the charge. So you won't see any charge. There won't be any electric field inside this conductor. If it's not a conductor, it will still partially attract the electrons, and they will screen the charge. So it won't be if you put some other electron somewhere else in your material, it will not feel this 1 over r squared electric field. It will feel a smaller electric field. And for example, it will be, if you take fourth quantum mechanics 2, there is an analysis of the helium. So it turns out that in the helium you have these two electrons, and the electrons, they kind of see something like 70% of the nuclear charge, because the other electron is basically screening the other 30%. Effectively, the other electron creates a 30% repulsion. So that's what we call the screen charge, in comparison with the Bayer charge or Bayer-Coulomb potential.
So I have a question about the derivation of the potential of the dipole. In the book we have the approximation, or they use the fact that R is much larger than D, but in mathematics of incorporating it, I couldn't get it. So
Which derivation?
first we added the potential due to the different layers, and then we then said that R is much larger than D. So the layer that is supposedly further and has a negative charge, with the denominator, we had maybe you can write it, or if you want, you can see it.
So we have the plus sigma, minus sigma. We take some area over here, another area over here. Their separation is D. The charge density is plus sigma and minus sigma. and we look at the potential at that point, or let me put that point over here. So let's call this one R plus, this one R minus. So the potential at the point R is equal to, due to this dipole, this small area elements only, it will be sigma times dA, dA being a very small area element over on the surface, over R plus minus sigma times dA, dA being the total charge, divided by R minus.
And you can say R minus is R plus ND.
R minus is equal to R plus plus.
ND. Normal vector.
Well, let's see, this is the normal vector. So R plus vector, R plus vector is equal to R minus. No, sorry. You're at R minus is R plus minus ND. Let's say that this is dV. So how do we relate R minus and R plus? And we will be assuming that R minus eventually goes to R plus. D will go to 0. And D is much smaller than R minus or R plus, both of them. So we have to expand, let's say, eventually we will be taking the limit D goes to 0. We can use R plus as our position vector. So let's see, R minus squared, we have to express everything in terms of R plus and D. So that will be our A. R minus squared will be R plus squared plus D squared minus twice R plus D times cosine theta. We are taking the scalar product. Now cosine theta is the angle between R plus and N hat. So this is our angle theta. And so R minus would be equal to R plus multiplied by 1 plus D over R plus squared minus 2 D over R plus cosine theta to the power 1/2. I just took the R plus out of the square root. R plus squared. And then since D is much smaller, eventually we are taking the limit that D goes to 0. This number over here is much smaller than 1. And so this is approximately R plus, R minus is approximately R plus times 1 minus D over R plus cosine theta, plus terms that are proportional to D over R plus squared.
How did we reach here? How did we reach here?
Well, we know that 1 plus x raised to the power n, if you just do a Taylor expansion, this is approximately 1 plus nx plus terms proportional to x squared. So I just multiplied that this thing over here by 1 over 2, and I ignored anything that is proportional to D over R plus squared, because that term is D squared, and eventually we have, let's see, if you look at this expression over here, we have sigma over R minus, and if we expand the R minus, 1 over R minus, we will get a term proportional to D, and D times sigma is finite. If you take the term D squared term just gives a contribution that is D times sigma. D times sigma is finite in the limit that D goes to 0, but then that term is 0. So in the limit that D goes to 0, that D squared over R plus squared terms will not contribute. So this is r plus minus d times cosine theta. So r minus is approximately this number over here. Now we can go back and write the potential. This is sigma times dA, 1 over r plus minus 1 over r minus. This is equal to sigma dA, r plus to the power minus 1 minus, well, r minus is r plus minus d cosine theta to the power minus 1. This is equal to sigma times dA over r plus 1 minus 1 minus d over r plus cosine theta to the minus 1. I took the 1 over r plus out. So dV is equal to sigma dA over r plus. Well, again, d over r plus is a small number. I can use the same expansion I used before. So this is 1 minus 1 plus d over r plus cosine theta. There is no minus 1. I already made the expansion. So these will cancel. So dV is approximately sigma dA over r plus minus d over r plus cosine theta, or sigma dA over r plus cube d times r plus times cosine theta, but this is nothing but d n hat dot r. So dV is minus sigma dA times sigma times d dA over r plus cube or r plus squared times n hat dot r hat. Well, sigma times d, we fix it to be d. So dV is equal to minus d times dA over r plus squared Of course, we need to sum this over all possible dAs. And the next thing left is just dA over r squared just turns out to be the solid angle. Questions? Well, I should bring a clock here. That's those noisy ones. Where you can hear the seconds.
You don't want the solution of the homework?
No, I don't.
Liste işte çözer misin?
We might. Yeah, if you understood everything, I can ask you questions. Okay. You didn't ask any questions on the capacitance. Let's look at what's the capacitance of a given system. Now, let's just assume we have two conductors. And such that one has a charge plus Q and the other one has a charge minus Q. And, well, they are conductors, so we know that the charge is only on the surface, there is no charge on the inside, plus the electric field on the boundary of this conductor is perpendicular to the conductor. Or the potential is a constant on the surface of these conductors. Do you agree? Do you know why? The electric field is perpendicular to the surface.
Because there was a component parallel to the surface, it will change the charge distribution.
It will, yeah. It won't be any more statics. So we are looking at electrostatics. So all the charges has moved to their final position, so they are not feeling any net charge anymore. So if there was a horizontal component, as your friend pointed out, there would be a net force acting on our charge, and they would start moving. But we say that since we are doing electrostatics, there's nothing moving. So the electric field lines, if you would draw them, they would kind of look like this. They can have some arbitrary shape. Now the question is this. So this was our previous configuration, the previous configuration of electric charges. Suppose we put twice the charge. So do you expect the shape of the electric field lines to change or not? How?
Because the charge distribution will be different.
The charge distribution will be different. So let's say rho at R, let's write this as Q times rho tilde of R in the first case. In the second case, since we are putting twice the charge, you are saying that the total charge will be 2Q, and it will have some other distribution. Okay? So that's your claim. Okay, the rest, do you agree? So there will be some other charge distribution and hence some other distribution of the electric field lines. Do you agree?
No.
Why not? What do you think is wrong with his argument?
Charge distribution. Okay, charge distribution will be different, but the draw tilde is some function, right?
Yeah, I'm just changing the normalization of rho such that the rho tilde of R integrated over the all of volume is equal to rho tilde prime of R integrated over the whole volume, and these are just 1. The total charge is Q, so I just factor it out, Q and 2Q, but the rho and the rho tilde and rho tilde prime, their integral is 1, so that we get the total charge. Well, of course, keeping in mind that this rho 1 or rho 2 denotes either the positive charge distribution or the negative charge distribution only. Because the total charge in both cases is 0. But your friend is saying that the charge distribution in the positive conductor and the charge distribution in the negative conductor, they will be different. So since they will be different, the electric field lines will also look different.
Charge distribution only depends on the conductor.
What do you mean depends on the conductor?
So take the conductor's shape.
Okay. But for example, why not, for example, if we put plus Q charge on this conductor, or when we add the additional plus Q charge, why don't they, let's say, concentrate over here on that surface area? Won't they? Or in that region or in some other region?
Is the charge distributed uniformly?
No, not necessarily. And definitely not uniformly distributed. The shape is not uniform.
I'm saying that if we have more charge and we have stronger electric field,
Okay.
it should attract more charge from the other plate, the other conductor, towards the first one.
Okay. So you are saying that eventually if we put sufficiently long charge, all the charge will be kind of concentrated at the point that is very close to each other. That's your argument, right? And he disagrees. So ask him why.
How can the positive charges accumulate the same quantity? They repel each other. The extra forces.
So they are attracted by the other.
So there's mainly the dates A and B. Okay. So the positive charges on A will be attracted to the negative charges on B. And vice versa.
How about the distances? I mean, they.
Of course, the distance is okay. So if you take one infinity far away, then adding more charges will not change the distribution.
No, I mean, in this question, the conductors are fixed. I'm not moving them around, I'm not rotating them, I'm not changing anything in the conductors. The only thing I'm changing is I just first put the plus Q minus Q charges, I get the electric field lines and hence the charge distribution, because we had already seen that once we know the electric field lines, we can determine the charge distribution. And then I add an additional plus Q and minus Q charge. So these additional charges will also distribute on these conductors. And the question is, will the shape, not the normalization, the total charges will be different in each one of the conductors, but the general shape of the charge distribution, will it change or not?
If we put more charge, it should be distributed more uniformly. Like you had said.
Take the case where date A is actually a point. Okay.
This is A, this is B. Okay.
Take the case where date A is actually a point.
B is a point.
Yeah.
Okay.
So then you will have stronger electric field coming from A. So the charge distribution at B will be more distorted.
So here is a claim.
I think electric flux will change if we double the charge.
Well, the electric field magnitude will definitely change. Well, at least the Gauss law tells me that if I imagine a Gauss surface enclosing only one of the conductors, since I'm doubling the charge in the conductor, the flux passing through this Gauss surface will be doubled. So the flux will definitely change. But what's about the shape of the electric field lines?
There is no electric field inside the conductor that is distributed to.
Well, we don't know. I mean,
Static.
eventually it will be static. I mean, when I add the charges, additional plus Q and minus Q charges, of course the charges will be moving around. They will not be fixed, but eventually they will settle in their final positions. And after that time, we have electrostatics.
We can assume that there is no charge inside the conductor.
There shouldn't be any charge inside the conductor. It's distributed on the surface.
And it distributes like the previous charges.
So you are saying, but you see, the question is this one. So let's say we have this conductor over here. If I put some additional charge, maybe, let's say I have this system. Let's divide it into two. Maybe when I first put the positive Q charge over here, well, half of it is over here, half of it is over here. This is the initial distribution, or let's say 1/4 is over here, 3/4 is on the other side. Then I put an additional plus Q charge. one way of thinking might be, well, there is more charge over here, so they will be pushing these additional charges to the other side. So there will be, let's say, 3q over 4 on this side, q over 4 on this side of this additional charge. So these are the additional ones that I add. So is this a valid reasoning? Or, let's say I have this configuration. When I add the additional charge, they also separate in the same way.
Reduced charges has no effect on pure charge.
Why not? I mean, they will.
There is no electric field inside.
Well, everything is on the surface.
That's-
Everything is on the surface. Nothing goes inside, as you said. But, I mean, here, just imagine three-dimensional regions. And when I say that q over 4 is on this side, I actually mean on the surface of that side. So which one is more likely?
Yeah, I found some first one.
Yes. You are claiming the first one. You are definitely claiming the
You can
first
also
one.
Use the superposition.
Okay.
But
So what will that tell me?
current distribution is in a static mode.
Current
The
is.
second,
Hmm?
second additional charges also take this distribution. The net charge, the net electric field would be 0.
Okay.
We have also a static.
So your claim is the first case or the second case is more likely?
They will be same distribution.
No, what do you mean? So you are saying it's the second distribution, the second one. So if when I put the first plus Q charge on this conductor, 1/4 to the surface of one side, 3/4 goes to the surface of the remaining, then if I add another plus Q charge, again the 1/4 will go to the surface that already contained Q over 4. Right? So you are claiming 2. So, okay, 1 for 2, 1, 2, and 3 for 1. And your first one. You have no idea, you just came. The first one. Well, you see, this is one of the examples where the majority is wrong. It's the second one. You see, we had this uniqueness theorem, which basically stated that if you have, we already know the divergence and curl of the electric field. Let's say this is the electric field corresponding to the charge Q. And we know the curl of the electric field corresponding to charge Q, which is, let's say, 0. And we know the boundary conditions. Or instead of working with the electric field, let's work with the potential. V corresponding to charge Q, it satisfies the Laplace equation outside the conductors. And delta VQ this is delta VQ is the change in the potential on the surface. This is equal to 0 on the surfaces. Furthermore, dVQ by dr or let's say the gradient of V is perpendicular to the surfaces. Well, we have one more constraint. Let's say the gradient of V integrated over a suitably chosen surface, let's say just the surface around the plus Q plate, plus Q charge, this should be equal to minus 4 pi Q. Okay,
Gradient,
hmm?
it's gradient, right?
This is gradient. This is what V of Q should satisfy. And there is a unique function that satisfies these properties. So that is our uniqueness theorem. Now, when we look at V of twice Q, we add this additional charge. It should satisfy the Laplacian outside conductors. Delta V of 2Q, the discontinuity should be 0 on the surface. The gradient of V of Q is perpendicular to the surfaces. And is 0 inside the conductors. And let's say we also know that so this is the potential created by plus 2Q and minus 2Q should satisfy all these constraints, these equations and the boundary conditions. And of course, V of Q goes to 0 at infinity. And similarly, V of 2Q should go to 0 at infinity. Well, the uniqueness theorem states that there is a single function that satisfies the second criteria, the set of criteria. There is just a single one. Well, let's see if we can guess what that function is. V of 2Q is equal to twice V of Q. You see, this function satisfies all these conditions. Its Laplacian is 0 outside the conductors. It's continuous on the surfaces. And this gradient is perpendicular to the surfaces, and it's 0 outside. And its integral over the suitably chosen surface is 2Q minus 4 pi to 2Q, and it goes to 0 at infinity. It satisfies all the criteria. But we know that there is a unique solution. If this is a solution, this is the only solution. But this tells me that the potentials, they have the same form. But if the potentials have the same form, you just take the Laplacian everywhere. That gives you the charge distribution. So the charge distribution have the same shape. So the answer is this one, the second one. So if you put up some amount of charge, and 1/4 goes to one side and 3/4 goes to the other side, if you double the charge, again 1/4 goes to one side and 3/4 goes to the other side. What determines whether it's 1/4 goes to one side or some other fraction is not really the charge that you are putting in. What determines how the charge is distributed is nothing but the shape of the conductor, and shape and how they are situated relative to each other. So, for example, of course, if you reduce the separation between them, more charge will be accumulated at the points that are closer to each other. Well, if they are separated further away, then the charge will be more or less more homogeneously distributed, let's say. But once you fix the geometry of your problem, the shape of how the charges distribute themselves is fixed. So it's just the total amount of charge that you are actually changing. Now, of course, just keep in mind that here, I'm not just putting some charges on one conductor. I'm putting charges on both of them, such that the total charge is always 0. If the total charge would change, of course, this would be the potential would look different. Or if the equality of the charges in these both conductors would change, then of course I will get some different potential. But as long as I keep the charges in the conductors equal and opposite sign, the distribution of the charges does not change as I add additional charges. So this basically tells me that the potential created by this charge distribution is actually proportional to Q times some, well, the potential at the point R, let's say. It's Q times some number, some function. Let's say, let's call it f of R. But this f of R depends only on the geometry of the problem. It doesn't depend on how much charge I put. It is independent of Q. That's what I mean by it only depends on the geometry of the problem. Now, these two conductors, we said that both conductors are equipotential surfaces. Since the electric field inside the conductor is 0, every point on the conductor, including the surfaces, they should have the same potential. And if you look at the change in the potential, well, since the potential at every point is proportional to the total charge Q, the change in the difference of the potentials between these two conductors will also be proportional to Q. And that proportionality constant is what we call the capacitance. So this is how we define the capacitance. It's the number, since F depends only on the geometry of the problem, the capacitance depends only on the geometry. Well, basically, 1 over C is nothing but delta F, or which is defined as F of R plus minus F of R minus. R plus or minus are just arbitrary points on the plus or minus conductor. Since which point I choose on each conductor doesn't make any difference, because F has a constant value on the positive conductor, it has another constant value on the negative conductor. So this is how we define the 1 over C. And okay, you will read in many places that it measures the capacity of a conductor, of a system of conductors, let's say, to carry charge. So what does it have to do with the capacity? Can't I just add as much charge as I like?
I have finite potential.
Hmm?
I usually have finite potential. I always have finite potential.
Why? Well, you see, there are these interesting devices called the van der Waals one de Graaff generators. I like them. Now what they do is, they basically have this conducting sphere. There is a belt. Well, this is a mechanical belt. It just rotates, and there are brushes here, and also brushes over here. Brushes meaning just there. You just take a wire and make sure that it touches this belt, this insulating belt. And you just ground this, let's say, one of the belts. And due to friction, some of the charges from these brushes will be transferred to the belt. And the belt being an insulator, it will just carry it to inside the sphere. And once it's inside the sphere and it gets in contact with the brush inside inside the sphere, it's a conductor. So inside the conductor, the charges will move outside. So the charge will go to the sphere, to the outer surface. And as you keep on, as the belt keeps moving, you will add more and more charge to your system. And if you add more and more charge, you don't really fix it at a constant potential. So in principle, nothing prevents you from adding more and more charge here.
And then charge will be equally
Will?
At a certain potential, air will become ionized in terms of the
Now that's one of the problems. It will leak. It will, there will be, if there is air, let's say, there will be what we call the electrical breakdown. So the air will become ionized and it will just conduct it. So if you, let's say, bring another sphere close to it and also ground it, you will see that after some point there will be some sparks between these two spheres. That's mainly because the electrical breakdown of the atmosphere. Now the electric breakdown is mainly determined by the electric field that you apply. So air can only support a finite amount of electric field before the breakdown. Well, let's see what the capacitance does. If you have a system that has a large capacitance, the potential difference in your system will be small, but the potential difference is proportional related with the electric field. If the potential difference is small, that means the electric field is small. So there won't be an electrical breakdown. If you put the same amount of charge on a system that has a small capacitance, well, the potential difference will be huge, will be larger, so the electric field will be much larger. So the system, there will be an electrical breakdown. So it is actually the capacity of a conductor or this configuration to hold the charges separate from each other. Otherwise, beyond a certain capacity, it will of course depend on the kind of the medium that you immerse your system. But assuming they are in air, let's say, beyond a certain capacity, you won't be able to put more charges on these plates because there will be electrical breakdown in your system. Well, now the way to calculate this capacitance is actually right over here. You put Q, some charge Q, on one conductor, charge minus Q on the other conductor. Calculate the potential difference created between these conductors. Because the Q will create an electric field. So once you obtain the electric field, you can determine the potential difference between these conductors. And once you know the potential difference, we already know that it should be proportional to Q. Take the ratio, and that will give you the capacitance. That will be the basic idea. Whatever the system is, this is always how you proceed. Put some charge. From that charge, calculate the electric field, or if you can directly, the potential difference. Once you obtain the potential difference corresponding to that charge, take the ratio that gives you the capacitance. Now let's do an example of that. The easier one, spherical capacitor. So basically, what we mean by a spherical capacitor is we get a spherical conductor. Inside, we put another spherical conductor. And put some charge plus Q on the outside, put a charge minus Q on the inside, or let's say the other way around. First, we have to obtain the electric field. What is the electric field inside the plus Q capacitor? Zero. What is the electric field outside the minus Q conductor? Again, zero, because if you just imagine a spherical, we know that since the charge distribution is spherical, the electric field should also be spherical. It should be radial. It should only depend on the radial distance. And if you assume a spherical Gauss surface outside, the total charge inside that surface is zero, so the integral of the electric field should be zero. Since the electric field is in the radial direction everywhere, the contribution to the surface integral will be always proportional to the magnitude of the electric field at that distance. And since it's zero, the magnitude at that distance should be zero. So outside also the electric field is zero. The only place where the electric field is non-zero is in between the in between these plates. Let's say these spheres have a radius A and B. So what's the electric field between these spheres? Let's say at this point, Q over R squared. This is the electric field in the R hat direction. Because we know that we are outside the inner shell. So if you are out of a spherical shell, it just behaves as if it's a point charge at the center. So that creates an electric field Q over R squared in the radial direction. We are inside the outer shell, but if you are inside the spherical shell, there's no electric field. So the minus Q charge does not contribute to the electric field. It's only the plus Q charge that contributes to the electric field, and it just behaves as a point charge at the center. The potential at that point is just Q over R, assuming the potential at infinity is 0. So the potential difference will be Q over A minus Q over B. So this is, by definition, Q over C. So 1 over C is equal to 1 over A minus 1 over B. And so C is equal to AB over B minus A. Do you agree? Well, we can also talk about the capacitance of a single sphere. Capacitance of a single sphere. Well, this is, in fact, just like this one, the previous example. Well, let's see. The inner one is A, the outer one is B. Sorry, did I make a mistake over here? A is the smaller one.
Sign of the potential.
Well, I'm not paying attention to the sign of the potential because by definition capacitance is defined to be a positive number. So that's why I am ignoring the signs. So delta V should be positive by definition of the capacitance. So 1 over C is 1 over A minus 1 over B, which is positive. Yes. Now, if you have a single sphere, not these two concentric spheres, you can just imagine it as the limit as the outer sphere goes to infinity. So we only have the inner sphere left. And hence the capacitance is equal to limit as B goes to infinity of AB over B minus A, which is just A. That's the radius of the sphere. So basically, if you have two charged spheres, when you put them in contact, they will share the charge proportional to their radius, because they should become equipotential surfaces when they are in contact. And if they are equipotential surfaces, their V's are the same, so the charges should be proportional to their capacitances, and their capacitance is given by their radius. So what about the units, by the way? This tells us that the capacitance has the unit of distance. Now, if you remember, we had defined the capacitance to be Henry. Yeah, we are just using a different unit system. Yeah, it was Farad, yes. But now, in this system, the capacitance has the units of length, not farad. Yes. Any questions?
I still don't understand why it has a name.
Why shouldn't it? Well, let's see. Let's look at the definitions. Q over C. Now, what's the unit of Q? Hmm? No? We are not using these systems. We are using the unit of Q is what's called the stat coulomb, which is, it was Newton meter squared square root. What about delta V? Well, let's look at it this way. Delta V times Q should have the units of Q squared over C. What's the unit of delta V times Q? What's the energy? Or let's say energy has the units of Newton meter, which should be equal to Newton meter squared over the unit of Coulomb. So Newtons cancel, meters cancel. So Coulomb, the capacitance, not the Coulomb, should have the units of length. So everything is kind of consistent. Now, the issue is why the capacitance has the units of length is because we are not using the unit Coulomb for the charge. We are using a different unit for charge. And we can just use whichever unit we like. Whatever unit system you use, eventually what you should obtain is for at least, let's say, for the sphere, the capacitance of a sphere is proportional to its length. The proportionality constant, it will depend on your unit. In this system of units, it's just 1. In some other system of units, it will contain, let's say, 1 over epsilon zeros or other factors of epsilon zeros. In some other different unit, the coefficient will be 1 over 4 pi or 4 pi. It's just a matter of units. So let me just briefly mention the method of images. Well, for next week you have chapter 2, but not that chapter 2, the only thing we didn't discuss are the examples. You should be studying the examples because most of the material is discussed in the examples in your book. Like the capacitance are discussed in the examples. And there's no separate section for capacitance. Similarly, chapter 2 is the Green's theorems that we had discussed in our first week, and also the uniqueness, but there are many other topics that it discusses in the examples. Now, many meaning it discusses the method of images. Again, the method of images, in a sense, is based on the fact that the solution of for a given charge configuration or charge area conductor configuration, the electric field or the potential is unique. The potential you can shift it by a constant, but the solution's electric field is unique. So if you find one electric field that satisfies your or potential that satisfies your equations and your boundary conditions by some tricks or tricks, then that is the solution. There's no alternative solution. There's no second solution. There's no reason to search for other solutions. The solution is unique. So let's look at an example. Now, the typical example would be we have an infinite conducting plane. We can set the potential to 0 on the boundary. Well, this doesn't, by setting the potential on this conductor to 0, we don't really lose about the general applicability of our results. Because also remember what Green's theorem tells us is that if you have some kind of a boundary with arbitrary boundary conditions on the boundary, and you might have some arbitrary charge distribution in your volume, which is enclosed within this boundary, to solve that problem, it is enough to solve the problem of a single point charge inside your volume with 0 boundary conditions, or constant derivative of the boundary conditions depending on what kind of a boundary conditions you have. So once we solve this problem, let's say of a single charge over there, this will allow us to determine the potential created by an arbitrary charge distribution in our volume and arbitrary boundary conditions on this conductor. Not necessarily the 0 boundary condition, just by using the Green's theorem. So we just stick with this simple example of a point charge in front of a grounded conductor. The potential should be 0 at infinity. It is 0 on this conducting plate. Or basically, the potential should be, the electric field should be perpendicular to this plate also, since it's an equipotential surface. So this is what we need to solve. But we already know a similar system. You see here, if you just imagine a plus Q charge, the electric field lines will look something like this. Well, we already know a system that has similar electric field lines. If you just imagine a dipole, you have a plus Q charge over here, a minus Q charge over here. This is your conducting plate. The electric field lines will look like this. Now, furthermore, since I have a plus Q charge and a minus Q charge, they are quite symmetric. On the middle, the potential will be 0. The potential will be equal to Q over, let's say, the distance from the positive charge, minus Q over the distance from the negative charge. So on this, on the dashed plane, the potential is 0 for this potential. At infinite distance, the potential is again 0. So this potential satisfies our boundary conditions. So this potential is 0 on our conducting plane. It is 0 at infinity. The only thing left is, does it satisfy our Laplace equation? And in this case, our Laplace equation is this one. This should be equal to minus 4 pi rho of r prime, rho of r. But we have a single point charge, so this is equal to minus 4 pi times the 3-dimensional Dirac delta r minus, let's say, r plus. So if we can show that the potential satisfies this equation, then we are done. We have one solution. We just guessed one solution. But we know that solution is unique. So since our, let's say, guess turned out to be a solution, it has to be the only solution. So we don't need to go and look for other solutions. Well, let's see if our potential, if this one, let's call this one the trial potential. It satisfies the boundary conditions. Let us look at it, let us act on it with the Laplacian. Well, R plus is the distance of R from the positive charge, and R minus is the distance from the negative charge. Well, if I act with the Laplacian, 1 over R plus just gives me a Dirac delta. So I have this three-dimensional Dirac delta, R minus R plus, minus 4 pi, the three-dimensional Dirac delta, R minus R minus. It almost satisfies my boundary, my Poisson equation, but there is this additional term. But you see, the problem is we are looking for a solution of our Poisson equation in a domain, in a region, in a volume where R is never equal to R minus. You see, this is our problem. We have this conducting plate. We are looking for the potential in this region, in front of this plane. So, because, I mean, you see, we have the boundary, we are looking for a solution inside the volume that is bounded by our boundary. Our boundary is this plate plus infinity. So we are looking at the solution in this region, on the right of the plate. But on the right of the plate, since R is never equal to R minus, this three-dimensional, the additional Dirac delta function is 0, exactly 0. So the trial is our solution for the potential, because it satisfies the Poisson equation in our domain. It satisfies the boundary conditions on the boundary of our domain. Since the solution is unique, it has to be the solution. So this is what's called the method of images, basically because just imagine this infinite plate as a mirror. If you are on this side, you will see your image on the other side at the same distance. Now, in this case, the image is negatively charged. So this is the basic idea of the method of images. Well, just like the Gauss law, it cannot really be applied in every circumstances, but if your problem is has some kind of a symmetry, then you can still apply. Like this one, or I mean, in the book you will be also discussing a charge in front of a conducting sphere. The sphere is quite symmetrical object, so you can use this method of images there, or there is an example also about not necessarily an infinite plane, but you take one conducting plane and another conducting plane with suitable angles in between. So for example, if the angle between is 90 degrees, just imagine having mirrors that are separated by 90 degrees. You will have 3 images. Or if the angle is, let's say, 60 degrees, then you will have 5 additional images. So here also you will get the additional 5 image charges, and the total potential will be the potential created by the charge you put plus the potential created by your image charges. So at least for such systems, there is a quite almost trivial way of solving the potential for these systems. Okay, this is what we will be discussing next week. I'm expecting you to review the Green's theorem also, and go over the examples and come back with more questions. Okay, this was kind of the first week, so you didn't really know what is expecting you. But at least I'm hoping that for next week you know what is expecting you, so you will be talking, answering, and asking questions. Okay, so have a nice weekend. See you on Monday, 8:40 unfortunately.